Y18 electromagnetic waves. Now we know four Maxwell's equations, two Gauss law and differential form, Faraday's law, and it's a differential form, and Maxwell-Ampere's law, and it's a differential form. In this section, we investigate the propagation of electromagnetic field in free space. Free space, no charge in space. For example, the space between the sun and earth, there is nothing. No charge, no current. Even in vacuum, electric field and magnetic field fills the space. So we have the zero charge density, it's zero current. These four equations, called Maxwell's equations in free space, is enough. They are enough to describe the propagation of electromagnetic field in free space. First, Maxwell noticed the product of permeability constant and permittivity constant is 1 over c squared, and c is now determined to be 299,792,458 meter per second, and this is exact. It does not change at all in free space. That is the postulate of Einstein's special theory of relativity. Now, the displacement current contribution only survives in the Maxwell-Ampere's law. From here, using this constraint, we find it is 1 over c squared time derivative of electric field. Because the CB and E are of the same physical dimensions, we multiply speed of light to the magnetic field. Then it becomes time derivative becomes c times time derivative. You know, the gradient operator, it is E1 hat, x derivative, and so on. This is c time derivative, this one, this gradient, and the c times time derivative, they are of the same dimensions of 1 over length. So we write down four equations, two Gauss law and two Kerr equation. This is Faraday's law and this is Maxwell's law. Heaviside, who developed this kind of Kerr divergence, and the vector calculus was developed by Heaviside, and he noticed the symmetry among these four equations in free space. We learned that electric field is replaced by speed of light multiplied by the magnetic field, and the C magnetic field is replaced with the minus electric field. In that case, these four equations doesn't change at all. Doesn't change at all. This is called the duality of Maxwell's equation. So why don't we replace electric field with CB? This one used to be there. Electric field CB, so CB, okay. And CB is to be replaced with minus E's. CB is replaced with minus E. Then it becomes a plus. Haha, this was here, the same. So magnetic field CB minus E, what we get? Oh, this equation. And the last one, Faraday's law, CB minus E, and ECB. So this negative sign moves to the right-hand side, then it becomes the Faraday's law. So this is called the dual transformation. On the dual transformation, Maxwell's equation is invariant. The four equation becomes the same set of equations. And actually, he found that this electric field, three components of electric field and three Cartesian component magnetic field, there are six independent components, and these six independent components are actually the six 0, 0, 0, 1, 0, 2, 0, 3. 1 0 1 1 1 2 1 3 2 0 2 1 2 2 2 3 3 0 3 1 3 2 3 3. There are 4 by 4. This is a 4 by 4 matrix called the field strength tensor, and this is a anti-symmetric under exchange of the two indices, nu mu minus. Then we have only six independent set of variables, and Maxwell found that these electric fields and magnetic fields are those six elements of this the anti-symmetric 4 by 4 matrix. So actually, you don't have to remember everything in here, but this is called the field strength tensor defined into four-dimensional Minkowski space, and these components, they are anti-symmetric if we exchange the row and column. These three are magnetic fields, and if you exchange the row and column, you flip the sign. Okay, so electromagnetic field they are not separable concept. They are just six components of a single object called the field strength tensor in special theory of relativity. And it was found that you are familiar with the Lorentz force. The electric field creates electrostatic force. Magnetic field applies a magnetic force on a moving particle. However, it is completely combined into a single matrix equation. In here, this matrix represents this field strength tensor. Even though you don't have to fully understand the structure, however, you have to remember that electric field and magnetic field are not separable, but six independent components of a single theory. So Einstein's special theory of relativity is great because by the time they were different theory, but they are combined into a single unified theory in nature. This is the first unification of fundamental force of electricity and magnetism. Okay, you will find more interesting materials in here if you click. You have to remember some simple algebra. So we have curl. If you compute curl, you need to introduce Levi-Civita simple to simplify the calculation, but you are already very familiar with the back cap rule. Back cap rule, A cross B cross C. Using this one, you can find that this curl vector field is gradient divergence subtracted by Laplacian of a vector field. So you will find this one is always a zero because in vacuum it is zero, and this magnetic field divergence is also zero. So we are more interested in the second term only. Now, let us find the equation of motion by combining the four equations of Maxwell. Faraday's law and Maxwell's law. We take the curl of both sides. And curl, according to this relation, because the divergence E and divergence B are both vanishing, we find this curl electric field is minus Laplacian of the electric field. And this is, if you take the curl, we can make use of this side. Then use this, you will find there's a second order derivative with respect to time. In a similar manner, this curl B will be minus Laplacian of B, and this will give the curl E, and if we use this curl E relation, again, it becomes the second order time derivative of the magnetic field. Therefore, these two equations reduces to a similar equation. This is wave equation. And from here, you have found that electromagnetic field, both the electric field and magnetic field, travels with the speed of light. Remarkable finding by Maxwell. So electric field, magnetic field, they are traveling with the speed of light. Next, we consider what's happening for the actual oscillation. For simplicity, what we already have learned about phase of second order linear differential equation by considering our RLC circuit or driven damped harmonic oscillator. In there, we learned the sinusoidal wave is well described if we use exponential function. So it is more convenient to use exponential function for the oscillating wave instead of a pure sine or cosine wave. They are equivalent, but much easier. The analysis becomes much easier when we introduce the exponential function. Okay, so a vector field, such as electric field or magnetic field, can be expressed propagating with the speed of light, can be expressed in this way, kx minus omega t. And here, the ratio of the wave vector and the frequency give the speed of light. First, why don't we take the curl? If you take the curl, it is a spatial derivative. So it takes care of k dot x only. The final result is just a multiplication of ik cross product. The reason is explained in here. If I take the time derivative, then time derivative, its coefficient is minus I omega. So time derivative will bring in minus I omega. Therefore, for example, divergence of V is ik scalar product. Laplacian V is ik squared, so minus k squared, same vector field. So why don't we introduce electric field propagating in space with the speed of light along the direction and hat? Then we can introduce the electric field's amplitude. This is a three-dimensional constant vector independent of time and space. B0 is another three-dimensional vector independent of x and t. From the four Maxwell's equation, we learned that both the electric field and magnetic field satisfy the wave equation. If you take the car, what we have to do is ik vector cross E0 exponential. And exponential cancels. We have 1 over C, CB, CB0 vector. Here, time derivative will bring minus I omega as a multiplication. So I cancels, it becomes a positive, and we have K cross E0, omega over C, and C multiplied by B0. From this equation, this Faraday's law, we have IK vector cross product CB equals 1 over C minus I omega E0, and exponential factor they cancel. Finally, we end up with these relations. From here, we find that wave vector squared is omega squared over C squared. In addition, these are triple scalar products. First of all, we remember divergence E equals 0 and divergence B equals 0. Therefore, K dot E0 should be 0 and K dot B0 should be 0. From here, we find that K wave vector is perpendicular to the electric field, and this K is also perpendicular to the magnetic field. So we are interested in the relative direction between the electric field and magnetic field. That is completely determined by this Maxwell's law and Faraday's law. The final result is that electric field behaves like x-axis and magnetic field behaves like the y-axis, and the vector wave vector behaves like the z-axis. In mathematics, there is no way to introduce a natural choice of the basis vector. That is arbitrary if you learn mathematics. And in physics, there is indeed nature gives you the fundamental basis vector for the XYZ direction that is completely governed by electromagnetism. And the propagating electromagnetic field in free space is along a wave vector. Electric field oscillates on a plane, and magnetic field is perpendicular to the electric field as well as the wave vector. This is a fundamental nature of electromagnetic field propagating in free space. In free space, in vacuum, even though there is nothing at all, only space, space is filled with electromagnetic field. That includes the visual, the light and radio waves and anything. Heat, infrared, ultraviolet, X-ray, it is called the Maxwell's rainbow. Maxwell's rainbow includes all kinds of electromagnetic fields that can propagate in space as well as vacuum. No other wave, such as a mechanical wave propagating along a loaded string or sound wave that propagates in the air, they cannot travel in free space. In vacuum, only the electromagnetic field propagates with the speed of light, always. Next, we study polarization vector and pointing vector. We learned that we could have introduced a phase, and the phase appears when we have a single derivative in the equation. However, that kind of operator appears in the damping term in the first damped harmonic oscillator. However, the equation, Maxwell's equation, even though it indeed has a single derivative with respect to space and time, finally we have found that they are satisfying the wave equation that are second order only. This wave equation do not have any single time derivative or single uh, spatial derivative. Therefore, there is no damping at all. So as a result, just like what we have already done with this result, addition of a phase between, relative phase between electric field and magnetic field is disallowed. Even if you include this you will find delta must be zero. So propagating electromagnetic field are always in phase. There is no phase shift like that. No, not at all. They are always electromagnetic fields propagating together are always in phase. So using in phase oscillating wave for the electric field and magnetic field, why don't we introduce a unit vector that is called the polarization vector? And you will find the electric field oscillates along a single direction. Magnetic field oscillates along the direction that is both perpendicular to the wave vector and electric field. And this is k hat cross epsilon hat, something like that. So E field, B field, and propagation direction. And actually, electric field does not have to be isolated all along this axis. There are two possibilities along this direction and that direction. So there are two transverse polarization. Transverse means it is perpendicular to the direction of propagation. We know what the energy density of the electric field is. We know what the energy density of the magnetic field is. And the electromagnetic field has the energy density in space in this form. And actually, they are traveling with the speed of light. So the energy propagation can be expressed as a kind of current density. This current represents the energy propagation. Energy propagation. Then usually current density is expressed in as a product of the velocity multiplied by the density. And you can substitute the electromagnetic field energy density into this rho and speed of light to this v. That is called the Poynting vector. Poynting vector S is defined by this 1 over permeability constant equals B. Equals B has the direction along the wave vector. And at the end of the day, you will find this is the speed of light multiplied by the energy density of an electromagnetic wave. And it oscillates. So it has a squared oscillation term. Its average over space or time will bring in 1 over 2, 1/2 factor. So RMS value for the amplitude can be defined like that. This differential operator appears in the wave equation. However, we know very well about the Galilean transformation. That Galilean transformation gives invariant equation for F equals ma. That is the fundamental equation of motion of Newtonian mechanics. However, if you make Galilean transformation to this operator, and you will find it is a straightforward calculation based on the chain rule you learned already. Finally, the final result, there's a breakdown of the shape of the operator under Galilean transformation. This is an explicit counterexample that Galilean transformation is a wrong transformation for the electromagnetic wave. The reason is that the electromagnetic wave travels with the speed of light, and Newtonian mechanics cannot explain anything about any particle that travels with the speed of light or very similar to the speed of light. So Galilean transformation does not work at all for the electromagnetic wave. This is the beginning of the Einstein's relativity. Our fundamental question is that is there any way to make this wave equation operator invariant under a generalized Galilean transformation that relates the two inertial reference frame having time and space? The fundamental mistake of the Galilean transformation is that time is absolute. However, if you introduce the combination, the mutual transformation between time and spatial component, then it is indeed possible to have the same operator. Because the physics equation must not be different in depending on the frame of reference. And indeed, the Lorentz transformation was found to be the exact space-time coordinate transformation rule that preserves the form of wave equation. By the way, that can be only explained that the speed of light doesn't change depending on the observer. Even though they knew very well about the mathematical relation already, but they were not brave as Einstein that the speed of light is invariant.